Right. Hello, folks. Let me get my pen going. And now we're going to talk about magnetism today. And there's going to be about two lecture sections on this because it's easy, but we've got a lot of concepts we have to cover so we can do this properly. So let's go ahead and start. All right, magnets. Should be, everybody should know this. This consists of two poles, north and south. So basically we have a piece of metal that may be a magnet, and that's probably a magnet, and it attracts other pieces of metal. And we have two poles. Basically, is that if we have something positive, we call it north and south, just by that's how it's always done. North is here, south is here, and actually the south is attracted to north and vice versa. So when we have our Earth, and here's our pole, this is the north pole, this is the south end of the magnet is drawn to the north pole. So this end always points north, and this end, which is the north end of the magnet, always points south. And this is how we figure out how things are magnetic. Now, in the material, we got magnetic domains, and basically they're a small group of atoms whose electrons spin in the same direction. And they're going to be these things are very, very small, from 0.01 millimeter to 1 millimeter in diameter and size. So let's take a look at what causes magnetism. We said that they're spinning electrons, and they have to have unpaired electrons. For example, let's look. If we look at hydrogen gas, H2, and the hydrogens are paired up, and there's no extra electrons in here. Both of these are paired up, and this is what we call diamagnetic. It does not have an electron magnetic field to it. Where we had O2 had some, it's paramagnetic because it has some unpaired electrons. And this is when we did the molecular orbital theory. This is one of the reasons why we use molecular orbital theory, because O2 is paramagnetic. It's attracted to a magnetic field. It leans one way or the other. So iron has, let me look at the periodic table. It has 6 electrons, 6 d electrons, 6 electrons in d, but 4 are unpaired, meaning that iron can be magnetized, can have a magnetic field. So basically we're looking at iron atom, and we got these 4 electrons that are unpaired. If they all spin in the same directions, they're multiplying the magnetic field together, and it can attract other magnetic fields. And how we can make the iron into a magnet, because you actually have pieces of metal that can induce a magnetic field to it. And you can do it by one or two ways. One is of having a material by a magnet, and that material will end up having a stronger magnetic field, or the electrons start aligning up with a magnetic field, or these unpaired electrons, and then that piece of metal will have a higher magnetic field. Or we create an electromagnet by taking a piece of wire, wrapping it around it, introducing a current, and next thing you know, the piece of metal is a magnet. And we were supposed to do this in lab, but we'll do it later. There are 2 types of magnets, hard and soft. Hard will not lose its magnetic field, but soft will. Basically, if you have a soft magnet, it will lose its magnetism over a period of time, especially if you hit it or heat it, cool it. Then you will jostle the magnetic domains. The electrons will start spinning in different directions, and next thing you know, the magnetic field will decrease. So we like to have hard magnets if at all possible, but if you have a soft magnet, all you have to do is introduce it with a stronger magnetic field or some electricity. Now, when we have electricity, those moving charges are actually electrons. So they are actually creating a magnetic field as they move. So moving electrons So we've got this wire and we got electrons moving, and it's going to have a magnetic field, and adjustments, deviations in the current will cause deviations in the magnetic field. And this magnetic field is circular. So if we have a wire, I'll draw it over here. We have a wire going up and down, and we have electrons flowing this way, and we're going to have a magnetic field come around the wire like this. And this is what we mean by magnetic field. So if we got wire, we can see it right here, is the magnetic field is all going around the wire like this. Closer in, the higher the magnetic field, farther out, the magnetic field will decrease. And to determine the direction of the magnetic field lines, use the right-hand rule. So grasp a wire with your right hand, your thumb out, and point in the direction of the current. And your fingers, as you wrap around, will point in the direction of the magnetic field. And if I do this properly, I'm going to discard these changes, and we're going to look at me. Hold on, I gotta do this. This is going to be interesting. Let's see if I can do this. All right, ladies and gentlemen, we're looking at the right-hand rule at this time. So what we need to do is a pen. This is going to be more wire, and the direction is towards the end of the writing end of the pen. So right-hand rule, take your thumb. Here's my pen. Sorry, get it in focus. Put my hand in my thumb in the direction of the pen. The current. Wrap my hand around it, and now the current is going this way. My fingers are going around this way towards you, and that's the way the magnetic field is going. So all the negative is going this way, positive is coming this way. So if I point this to you, I gotta make sure I keep my hand up. My thumb is pointing towards you, and my hand is being wrapped around clockwise direction. If we look at the other way, my thumb's pointing towards me, and my hand is wrapped around going counterclockwise, and from my point of view to your point of view is going clockwise. This is the right-hand rule. One more time. Wire. Right hand. Ta-da! Fingers, thumb pointing towards in the direction of the current. Hand wraps around. Current's going this way. Electromagnetic field's going this way. And that is the right-hand rule. All right, ladies and gentlemen, we're finishing up this lecture now. You see me switching between my PowerPoints and myself. And so we're going to continue on with wire loops. And we'll almost be done with this part of the lecture. So let me change to a pen color that we'll can see. So loops of wire, when you put electrical current through it, will form a magnetic field, and it will have north and south poles. A device called a solenoid uses these properties to control doors. And then, so what we have, so if we have a loop, we'll have a magnetic field, and the magnetic field is going to end up going this way. So this is north, and this is south, and now we have a magnetic field that is produced by the electricity moving electrons through this wire. And this is key. This is how we used to make switches back in the old days, and actually we may still do solenoids. You press a button, it connects a circuit, and the circuit either charges the magnetic field, or in some cases, press a button to break the circuit to turn the magnetic field off and release whatever it's holding. So we have two ways to manipulate magnetic fields, with a code or without. And so this is what it should look like. And we're going to stop right here for today.